Hello everybody, welcome to day 2 of online finite math. Today we're going to keep talking about apportionment. I have a couple of things I wanted to say first though. So I'm sure you've all heard the rest of the semester will be online. That means we definitely won't be having a second midterm exam. I will replace it with a project. Haven't posted that project, but I have it. I have it all laid out and it shouldn't be too painful. I think it should be good. You'll learn lots about financial math that way, probably more than you would half watching my video lectures. So, yes, that's that. On the note of a final exam, I might replace that with a project as well. So, things I can say definitely, the second midterm will be a project. Things I can say probably, the final exam will also be a project. But I think we're sorting that out. I'm curious what other professors will do. Yeah, still playing it by ear, I suppose. But yes, as far as we're concerned, I will post a quiz this afternoon or right after this class, and normally those will be due on Thursdays. I think I'll make this one due a week from today, just because nobody's I don't know, because this is the beginning. If you still want to get it done by Thursday, by all means, be my guest. But I will make it due a week from today, and then a week from today I will upload another quiz, but then I'll start making them due on Thursdays once we get into a routine of doing class this way. Alright, so that's my plan. Let's start talking about apportionment again. Good. Alright, I'm gonna flip around to my screen here. And let's recall what we were talking about last class. So, last time we defined what apportionment was. I won't go through everything again, but I'll recall the setting for apportionment. Here, why don't I give you a little taskbar that says what we're doing today. So today, recap of sections 4.1 and 4.2, and then we will cover section 4.5. Section 4.5 is called the Huntington-Hill method, or the method of greatest fractions. Equal proportions. The method of equal proportions. This is the method that we use in this country right now since 1941, when they passed the Apportionment Act. We will learn about the method that is currently used in our system. Method of equal proportions. Okay. So, recall the setting for apportionment. What is apportionment? You have apportionment is the division of objects amongst parties which don't necessarily have equal weight. Remember, this is like a weighted fair division problem, pretty much. The division of objects amongst parties which do not necessarily have equal weight. So when we talked about those fair division problems, I mean, technically we could have been talking about them as apportionment problems too. It's just that it's not interesting to talk about apportionment when everybody is weighted equally, because then we might as well just say division. That's kind of the root of the word here. So for us, this is the division of seats. Say in a House of Representatives. as in a House of Reps. Amongst states, using a method based on population. This is both total population and the population of each state, which are closely related. Because remember, the total population, you just sum up the populations of every state. Good. So, now, in order to apportion the seats, or to decide how, in order to decide how to apportion these seats, so the first thing that we need to know is how many people correspond to one seat, right? So if we have like 10 seats and 100 people, then 10 people should correspond to a seat, approximately. This makes sense. You just divide the total population by the number of seats, and you find out how many people correspond to one seat. So we need to know how many people correspond to one seat. This is the standard divisor. SD, which is equal to the total population over M, where P is the total population and M is the number of seats. Right? Divide the total population by the number of seats, and you get how many people, what population corresponds to a single seat. Okay. So once we've found this, the standard divisor, then we can figure out approximately how many seats a state should receive. Then we can figure out how many states, or how many seats a state should receive. And remember, this we called the quota of state A, say, and that was the population of that state divided by the standard divisor. So if the standard divisor is how many people correspond to one seat, and then you take the number of people in a state and divide it by how many people correspond to one seat, you should get how many seats that state deserves, right? So these are, once you think about it, once you think them through, these are pretty intuitive ideas. Yeah. So should, and remember that this is a should receive because oftentimes this will be a decimal, but we can't give away a decimal, we can't give away a decimal or a fraction of a seat. And so what do we need to do? We need to find a way of rounding this quota so that each state gets an indivisible, like a non-fraction number of seats, a whole number of seats. So it might seem obvious how to round a decimal to the nearest whole number, but if we round every decimal to just the nearest whole number, we might end up giving away more or fewer seats than we actually have to give away. This quota is usually a decimal, but we can't give away a fraction of a seat. Figuring out how best to round the quotas is basically the study of apportionment. apportion methods. Remember, if you check video 4.1 for y, normal, rounding doesn't work. Okay, so we need to figure out a way to round off the quotas. So as a history, in the history of the United States, we tried a lot of stupid things until we found a good answer. In fact, I'm going to tell you about our good answer today, and it wasn't until 1941 that we put it into place. A bit of U.S. history. So we used strange methods from 1792 until 1850. Our House of Representatives had no fixed number of seats. And so this made the apportionment methods quite strange. I mean, it resulted in a lot of funny things happening, and we won't even study that. For our Hamilton method, what we call like the first apportionment method, was actually put into place in 1850. So in 1850, we fixed the number of representatives. And we thought that we had a good method, which was Hamilton's method. Now, Hamilton's method, I'll do a quick recap of, because but I talked about that in the last video. So from 1850 until 1911, when in 1911 we found the Alabama paradox. Someone found the Alabama paradox. I recommend that you go and read those scans that I posted on Blackboard, the scans from the book by Monmonier, because it's he gives a really good description of the Alabama paradox, which I think is very well geared towards, it's not a particularly mathematical description, it explains it very well, I think, what happened. And I gave a mathematical explanation of the Alabama paradox in the last video lecture. Though things were simplified, numbers were made nicer. Monmonier gives you the actual numbers, and I will talk again about the actual numbers in the Alabama paradox in the next video. But for now, really what you need to know is that the Hamilton method ends up favoring states with larger populations. And so what Alabama found is that when the number of seats in the House of Representatives was raised by 1 or 2, Alabama ended up losing a representative in the House. And they thought, and that's paradoxical. There's no reason why adding extra representatives to the House should make a state lose some representatives. But that's exactly what happened. And if you go back and check lecture 4.2, you'll find that paradox. So in 1911, we found Alabama paradox. Check video 4.2 and scan of pages from Bushmanders and Bullwinkers. Good. But I can just give a quick recap of Hamilton's method, because I'm not sure that I explained it terrifically last class. So basically the method is as follows. Hamilton's method. So actually I'll say recall Hamilton's method. Recall Hamilton's method. And so what that consisted of was assign each state with a quota less than 1 a single representative. Remember, this is like Vermont. This is what happens here. We don't quite have a population worth getting above the standard divisor. And so since the standard divisor, remember, is how many people correspond to a seat, if we don't have that many people in Vermont, we don't have enough people to correspond to 1 seat. However, we should still get some representation. So this is why we give each state with a quota less than 1 a single representative. Okay. Then round every other quota down. So no matter what, even if a quota for some state that was slightly bigger than Vermont, let's say, I don't know, so if there was a state with a quota of 1.7, they would also be assigned a single representative at the beginning. So Vermont may be with a quota of 0.5, and another state with a quota of 1.7 would both receive a single one, because either you're rounded up if you're less than 1, or you're rounded down if you're any bigger than 1. Round every other quota down, i.e. give each state its lower quota L. And because we rounded everybody down, we will have some surplus seats, and so we're going to then assign the surplus seats one at a time to the states with the highest remainders, fractional parts, residues. Remember, these are all pretty much words for the same thing. So a quick example is if we have states A and B, and the quota for state A, say once we calculated the standard divisor, was maybe 3.42, and then maybe the quota for state B was 4. Let's make it a nice even number, so then 5.8. So then in total, this gives how many? 8 seats? 8 seats. Okay, well, and so now we would round both of them down. So then the lower quota of A, so we'll give A 3 seats, and we'll give B 4 seats. And then we get 4 plus 3, this makes 7. So we have 1 surplus seat. And we'll give it to the one with the highest fractional part. So we look at the decimals. Now we forget about the 3 and the 4. We say, okay, well, state B has the higher decimal. So because state B has 0.58 and state A has 0.42, 1 surplus seat goes to B because 0.58 is greater than 0.42. Does that make sense? Well, good. Okay, and I told you this posed a problem. However, this method favors states with higher populations. Why is this? Well, you can kind of see it that if you had if your quota was 1.5, say, well, then 0.5, the fractional part, is actually like a third of the total value of the quota. Whereas if your quota was 100.5, now that 0.5 is a really small amount of the total number of seats that you should get. Another way of thinking about this is like, if you only are assigned 1 seat, but you could have been assigned 2, that's a difference of like twice as much representation that you're missing out on. Whereas if you had 100 seats, but you could have been assigned 101, that difference isn't going to make that's not going to make as much of a difference, right? So the difference. So why don't I say? So if Q sub A is 1.5 and Q sub B is 100.5, then rounding down affects A much more than it does. This is basically the reason. Okay, so now that we've done that recap, we can start on Huntington-Hill. So this will be section 4.5, Huntington-Hill method, aka equal proportions. I believe it's in the Constitution as equal proportions, or sorry, in the it should have been an amendment. Yeah. Proportions. Okay, so in 1941, so after 1911, when they found the Alabama paradox, they returned to a previous method which was slightly flawed, but slightly less flawed than Hamilton's. So from 1911 until 1941, we returned to a slightly less flawed apportionment method. But in 1941, Congress passed the 1941 Apportionment Act, which did two things. One, it fixed the number of representatives. I'll just do reps at 435. And two, it designated this method that we're about to talk about as the official apportionment method of the United States. Designated equal proportions as the official apportionment method of the USA. Good. So this is more complicated than Hamilton's. I can't describe it in I can describe it in 3 nice bullet points, and I will, but it is slightly more complicated. And in order to talk about it, we need to talk about a new way of rounding. This might seem weird, but because we have to fix this problem, right? We don't want to round everybody just down, because 0.5 means more to state A than 0.5 meant to state B here. So We have to find a new way of rounding, but we know we can't round normally because we already showed that that doesn't work. So we introduced the concept to understand this method. We introduce the concept of geometric mean. This is basically redefining the cutoff point where we round. So usually we round at 0.5, right? If you're bigger than or equal to 0.5, is if your fractional part is bigger than or equal to 0.5, then we'll round you up. And if it's less than 0.5, we'll round you down. This geometric mean is a different number, which is going to be quite close to 0.5, but is going to be slightly smaller, and it's going to be get closer and closer to 0.5 as the population gets bigger and bigger and bigger. So basically what this means is if you had been assigned a quota of, if your population should give you a quota of 1.5, then maybe actually we'll round you up instead of rounding you down like Hamilton's would have. Here, I'll talk about it. Even a quota of 1.48 might be rounded up in Huntington-Hill rather than Hamilton's method. Okay, so what is the geometric mean? Well, the geometric mean is basically just a formula. The geometric mean of two numbers, A and B, is, we'll say G of A comma B, and this is going to be the square root of A times B. And so basically what we're going to do is we're going to take the two numbers. So if our quota was 3.42, say, then we'll take A to be 3 and B to be 4, and we'll find the geometric mean by taking the square root of 3 times 4. Good. So let's just do some examples here. I'll make a note. This number, when B is equal to A plus 1, which is what it will be in our case, is always irrational. And remember that an irrational number is one that it repeats the decimal. Is the irrational numbers are the ones on which the decimal goes on randomly forever. I'll just say randomly, like there's no pattern. It doesn't repeat. So it never repeats and it goes on forever. Okay, so let's do a couple examples just to figure out what on earth I'm talking about. So, example. The geometric mean of 1 and 2 is G of 1, 2, square root of 1 times 2. This is just the square root of 2, which is like 1.414 repeating. We'll generally round these numbers to 3 decimal points. And so let's try some others. What about 2 and 3? G of 2, 3 is the square root of 2 times 3, square root of 6, which is 2.449 something. Blah, blah, blah. Let's try it again. G of 3 and 4, the geometric mean of 3 and 4 is the square root of 3 times 4, square root of 12, which is 3.464 something forever. Okay, So what we can notice about this is that the geometric mean is kind of approximately halfway in between these numbers. So it's not quite halfway between these numbers, it's a little bit less, but it's approximately that. So the geometric mean of 1 and 2 was 1.41, it's like a little bit less than 1.5. Same with this, geometric mean of 2 and 3 is 2.449, it's like a little bit less than 2.5. Geometric mean of 3 and 4 should be a little bit less than 3.5. So the geometric mean of A and A plus 1, this will be our lower quota and our upper quota, really, is a little less than A.5. And it gets closer and closer to A.5 as A gets really, really big. Good. And so now we can talk about the Huntington-Hill rounding rule. The Huntington-Hill rounding rule basically says round using the geometric mean. Instead of like some number 0.5. Okay, so let's give that a go. Given, this is the definition, given a quota Q, the cutoff for rounding is given by C is the square root of L times U, where L is our lower quota U is our upper quota, sorry. Okay. So if Q is less than C, then Q is rounded down to L. Q is rounded up. Good. And so that's really the whole, I mean, you should take a little bit of time to think about this and go through some of the exercises in the book. But this is really the entire thing of it. The rest of the Huntington-Hill procedure is quite simple if you know how to use this rounding rule. Good. So I'll draw a little picture maybe. If on our number line we have our quota somewhere here, and here's our lower quota, our Q rounded down, and here's our upper quota, Q rounded up, then using conventional rounding, then we just take this L plus U over 2 to be the cutoff for conventional rounding. Good. But we're not going to use L plus U over 2. Remember, this is what the actual average of L and U is. That's what gives us 0.5. In between 3 and 4, we get 3.5. 3 plus 4 over 2 is 7 over 2, 3.5. For Huntington-Hill, we're going to get a number which is a little to the left of that line. So now we have L and U, and instead our cutoff will be the square root of L times U. Cutoff for Huntington-Hill. Okay. So you can ask me questions in the near future if that's confusing for you. But why don't we do an example? Why don't we do an example for now? So we're gonna use these calculations here. We will come back to those, and it might not hurt to make a little table of them, though you can always calculate it again with your calculator. So using the previous calculation of G2, 3. Why don't we do a quota in between 2 and 3? If Q sub A is 2.48 for some state A, well, under the Hamilton's method, this would be rounded down. I mean, under Hamilton's method, everything would be rounded down. But even under normal rounding, round down to 2. But let's think about this. What was G of 2, 3? Well, this was the square root of 6, which was what? 2.449. Blah, blah, blah. Okay. Well, now 2.48 is greater than 2.449, even though it's less than 2.5. We have an 8 in the second spot here and a 4 in the second spot here, and so we round 2.48 up to 3. That's weird, right? But this is why we're doing examples, because under a normal method, 2.48 would be rounded down. Under this method of equal proportions, because I keep on getting mixed up between Hamilton and Huntington-Hill, and I'm just tired of it. So we're going to talk about equal proportions and greatest fractions, because that's what people actually call these things. Good. If Q sub B is like 2.3 or 2.4, then we still are going to round down. Then because we're still less than the geometric mean, we still round down. Because 2.4 is less than the geometric mean of 2 and 3, which is 2.449, blah, blah, blah. Good. Okay, so what are we going to do next? Let me just do, what if our quota was higher? What if Q sub C was like 42.49? Then what? Well, good thing I calculated. Well, the geometric mean of, what are the two numbers we're going to take the geometric mean of now? So why don't I say L is going to be 42, right? The lower quota. U is going to be 43. So that means that the geometric mean of 42 and 43 is going to be the square root of 42 times 43, which is the square root of 1806, which is like 42.497, blah, blah, blah. Notice how close this is getting to 42.5. As our numbers get big, only in the 40s, this number gets really, really close to just normal rounding. But never quite reaches it. This is like an asymptotic relationship. As our numbers get infinitely big, this will never actually reach 42. This will never actually reach 0.5. The decimal will always be a little bit less, but just a little bit. Okay, so now we just compare these two numbers. Well, now we have this number and we have this number, and if our quota is less than this number, we'll round it down. And if our quota is more than this number, then we'll round it up. Well, 42.49, that is less, because this is like 42.490, really. This is less than 42.497, whatever comes after that. So C gets 42 seats. The lower quota. Okay. So this is really why, I think I've already said it, this is why this method is better than Hamilton's method. It's because for a higher value of C, or for higher quotas, the value of our cutoff gets higher, gets closer and closer to our number 0.5. And so because bigger states get bigger cutoffs, we kind of take care of the favoring, of bigger states that Hamilton's method gave us. Because now a smaller state has a higher chance of being rounded up than a bigger state, which has a higher chance of being rounded down. And that's what we want. That's what makes things equal. Good. So now I can kind of write what the method is. So the method, and this is where I throw another little wrench into the plans. Find a suitable divisor D. This is usually going to be our standard divisor. But there are a few things that can go wrong where we could apportion, where using the standard divisor we might apportion an extra seat or one too few seats. And so sometimes we have to kind of mess with our standard divisor a little bit to make it work right. This is usually the standard divisor. But sometimes we have to kind of fudge the standard divisor a little bit. We have to make SD slightly smaller or larger to apportion the correct number of seats. I won't really go into that very much because I think it's kind of boring. But you can kind of think of this like, remember when we did the normal rounding on Peridor in our first example? Well, we ended up trying to give away more seats than we had to give away in the house. And so, so that was a problem. And in certain circumstances, we can fix that problem by simply just making the standard divisor a little bit bigger or a little bit smaller. Then we can make the quotas go on either side of the cutoff point, and then we can make some of them be rounded up, some of them be rounded down, and eventually we reach the right number of seats that we're giving away. So that's basically what I mean by a suitable divisor, and I will give you the suitable divisors for the most part. I won't make you calculate them because it's not even calculations. So, but sometimes we, So I will give you the divisor to use because calculating using guess and check is a bore. Good, that's what I think. Okay, and then the second bit to our method is simply find the apportionment of each state by rounding its quota using this rounding rule that we were just talking about. So find the apportionment of each state by rounding its quota using this Huntington-Hill rounding rule. Okay, and as it turns out, this will work out every time. I mean, provided we find the right divisor D, but there always exists a divisor D which is pretty close to the standard divisor, and which works when we use the Huntington-Hill rounding rule to apportion each state a good number of seats. Moreover, it doesn't produce paradoxes. This method, even though it's not perfect, and maybe in the future we will find other problems with it, it doesn't produce these big paradoxes like Hamilton's method did. So that's a big thing. Even though this method is not perfect, and we may find flaws, in the future, it is better. So at least it does not produce paradoxes like Hamilton's. Okay, so let's just do a quick example, and then I'll leave you to it. Okay, so here's an example. I won't do Parador again. I'll do a different country. So how about Parador's neighbor? Parador's neighbor, we'll call, what's its name? Guayuru. Has states A, B, C, D, and E, with populations listed below. Okay, well, let's list those populations. Let's make a little table. Okay, let's do state A, B, C, D, E. And then here on the next one, we'll do their populations. And we'll make more columns as we need them, but I think we'll have probably this one. Okay. So if we have state A, B, maybe I should have made these closer together. Okay. So this will be A, B, C, D, and E. This is state. And here we'll put their populations. So the state population of A is 34,800. Population of B is 104,800. Everybody's got 800s at the end. Then we have 64,800, and then we have 140,800 and 54,800. And I'm taking your book's word for it that this gives a total population P of 40,000. Sorry, I should not take anybody's word for that. It should give a total population of 400,000. Okay. So if P is 400,000, and let's say they have 40, M equals 40 seats in the house. So how are they going to apportion these 40 seats? Well, let's first try, I'm going to give you a hint, the standard divisor will work in this case. Let's find the standard divisor, which is the total population over the number of seats. So this should be 400,000 divided by 40, which is exactly 10,000. So this is a nice, easy standard divisor to work with. 10,000, you can just move decimal points over. In this scenario, SD is a suitable divisor. Okay, so let's find some quotas then. So remember, how do we find the quota? Q sub I is the state's population divided by the standard divisor. So when we divide by 10,000, remember this is basically just moving the decimal point over 1, 2, 3, 4 places for the 1, 2, 3, 4, 1, 2, 3, 4 zeros in 10,000. So our quotas will be 3.48, 1.0, sorry. 1, 2, 3, 4. We'll get 10.48. Here we'll get 6.48. Here we'll get 14.08. Here we'll get 5.48. And this will all add up to 40, just like we expected. I'll let you check that if you want to. Good. The quota will always add up to the total number of seats when you sum everybody's quotas, because we find the quotas by dividing the total number of seats, by dividing a state's population by the total population over the number of seats, which is like multiplying the sum of all the states' populations by the total by the number of seats over the total population, so you cancel those things out, and you're left with just the number of seats, 40. Good. Okay, so now let's find the cutoff points. So let's find some geometric means. Huntington-Hill cutoffs, i.e. geometric means. Okay, well, lucky for you, I've calculated them, but remember that this is like, if the lower quota here is 3 and the upper quota is 4, then the geometric mean C is the square root of lower times the upper, which is the square root of 3 times 4, which is the square root of 12, and that's precisely 3.464, blah, blah, blah. Okay. I won't do that for every one of them. I'll just write them down. So the square root of 10 times 11 is the C is the square root of 110, and this is 10.488, blah, blah, blah. Here we have C being the square root of 6 times 7, which is going to be 6.481, blah, blah, blah. And here we're going to get 14.491, something, something, and 5.477, something. Okay, so now that we have those cutoff points, let's see whether we round up or round down. So round to 3.48 is more than 3.46. So 3.48 goes up, and we get 4. Isn't that strange? 3.48 gets rounded up to 4. This should be a kind of strange thing, but it works. It works really well in this scenario, actually. 10.48 is a little less than 0.488. So this one is going to get rounded down. Okay, so that's going to get rounded down to 10. Even though this was 0.48 and this was 0.48, because 3 is smaller, it's got a higher chance, it's got a better chance of getting rounded up than a bigger number, even if it's just the difference between 3 and 10. This is a really good example of why the geometric mean doesn't favor, it gives a little bit more strength to the smaller states, because here it gives the smaller state an extra seat, where the same residue would give a bigger state, one fewer state seat. That's the whole idea. So 6.48 is less than 6.481, and so we'll round it down to 6. 14.08 is definitely less than 14.491, so that gets rounded down to 14. And 5.48 is bigger than 5.477, and so that gets rounded up to 6. And if we sum everything up here, we should get 20 there. Oops. So we'll get 20 there, and 10 there, and 10 there, and that makes 40. Exactly what we wanted. Good, so we're happy. Huntington-Hill worked here. Perfect. So in the end, this is our final apportionment. This, our final apportionment. And we're all happy. And this is actually, like I say, this is exactly how our system works in this country at the moment. Now, before I leave you, I want to say one quick thing about this suitable divisor. If we had just changed a couple of populations, so here I'm going to copy this table. Copy the table, and I'm going to paste it here. I know this is easier for me than it is for you, for sure. I'm going to make it a little bigger so that, yeah. Okay. So now let's say that we had changed our populations just a little bit. So now, why don't we say, we won't change our total population. Our total population will stay at 400,000. But why don't we just make B's population a little bit bigger? So we'll make we'll give B and C 300 more people. So this one will go up to 105, 100. And this one will go up to 65, 100. And so we added 300 people to states B and C, and let's say that those people who just moved to states B and C both came from state D. So we're going to take 600 people away from state D and bring it down to 140, 200. Okay. Well, one would think that this doesn't change too much, and in the end it won't change too much about how the seats are apportioned. But it will change a couple little things. So let's try. If we use the standard divisor, so now 600 people left state C and moved, and 300 moved to B. Sorry, 600 people left state D. 300 moved to B, 300 moved to C. Using the standard divisor for quotas, well, that was a pretty simple process. Remember, we just messed with the decimal point. So this one is going to change to 10.51. This one is going to change to 6.51. And this one's going to change to 14.2, right? 14.02. Okay, nothing else will change in this quota column. All is still good, still adds up to the number of seats. And our Huntington-Hill cutoffs are not going to change either, because remember, those just came from taking the square root of the lower quota times the upper quota. So the only thing that's going to change here is what we round to. Well, A didn't change, so we'll still round to 4. But now 10.51 is now bigger than 10.488. Look at this. So that's 10.51 is now bigger than 10.488. And so now we're going to round 10 up to 11. I'll put it in blue so you see what's changed. And similarly, C was now 6.51, bigger than 6.481. And so C is also going to get rounded up to 7 now. And D, which was already rounded down, is still rounded down and nothing changes. But look what happens. We just added 2 new seats to our apportionment. And so if we sum all of these things up, now we should get 42. Weird. Well, we can fix this. This isn't the end of the world. And we fix it by just by just changing the divisor. So instead of dividing by 10,000, now if we divide by a slightly higher number, then our quotas will be slightly lower, and we will round slightly more things down, and we can get to 40 seats again. So using the the standard divisor for quotas, yields, so means we give away too many seats. So if we use a slightly larger divisor, say 10,030 instead of 10,000. Well, if we use that slightly larger divisor, now everything works out. And I'll just rewrite that table using divisor D equal 10,030 to calculate quotas Q equal to Q sub I is population of a state divided by D instead of the standard divisor. This is that's crucial. Good. So now that we've got that, I can copy this table again. Let me just paste it in there. And well, I'll show you what the quotas change to. Now the quotas all turn into different numbers. They still add up to 40, of course, but good. So now this quota will be 3.47. Notice a little bit less than what it used to be. This one will be 10.479, 6.491, 13.978, and 5.465. These still will add up to 40 because they're just partitions of all of the seats. And our Huntington-Hill cutoffs will not change. These are still just the geometric means. And except for that 13 and 14. So now this one will change. Square root of 13 times 14 is c, and that is, well, it's 13.4 something, and we know that 13.97 is definitely bigger, so that will get rounded up to 14 there, so that won't change. And this geometric mean won't change either. Okay, so now how are we going to round? Now 3.47 is bigger than 3.464, so that's good, round up to 4. 10.479 is less than 10.488, so we round down to 10. 6.491 is bigger than 6.481, so we're going to round this one up to 7. This one is smaller, or this one is bigger than 13.5 even, so we're going to round it up to 14. And finally, this one is a little bit less now than the geometric mean, and so this one, state E, is actually going to get rounded down to 5. And all is still well. We rounded this one up instead of down, and this one down instead of up, but in the end, we've apportioned 40 seats to all of the states. And that is how Huntington-Hill works.